A function is like a machine. It has an input and an output. An input and an output. So you put a value into this machine, which we'll call a function rule, and it uses the rule to produce an output. Now, a function is a relationship in which every element of the domain has exactly one output in the range. So the key is that every element in the domain is used. Every element in the domain, I'll just highlight that, domain, so you can see where we're going with this, has exactly one output in the range. So you must use every element in the domain, and you can only use that element one time. It can only have one output. So when we're looking at this first example, is this a function? And that's what we're going to ask ourselves on all of these. Is it a function? First, every element of the domain needs to be used, and when it is used, it can only have one output. So we look at this first example. There are two elements in the domain, B and G. Only B is being used. So B is being put into this rule, and after it has the rule applied, its output is U. So one output of U. However, G is also in the domain. It's an element in the domain, and it's not being used, and every element has to be used. So therefore, this example right here is an example of not being a function. So this is not a function. And the reason being is every element in the domain needs to be used. So we'll just say every element in domain. And it has to be used only one time. Okay? I'm going to show you an example of when every element is used, but some may be used more than once. Let's go over here to our right. We have this example right here. So you need to draw these arrows on your notes. This is the given problem, exactly what you see on the screen. You've got a domain and a range. There are two elements in the domain, B and G, and both of them are being used because they both have arrows coming out of them. So the arrowhead signifies the output. So the arrowhead is this part right here, and it signifies the output. So the input is B, the output is S. The input is G, and the output is, whoa, two different outputs. We have a T for the output, and we have a Z for the output. So this is an example of not being a function, but a different reason than the first one. So this is not a function, and the reason here is an element in the domain is used twice. And I'm going to highlight for you so that you can see. Let's make that a orange highlight. So an element in the domain is used twice. So the domain is used twice, and that would be this guy right here. And exactly one output right there. Okay, let's look at another. Okay, here's an example. We've got two elements again in the domain, B and G, and then we've got our range. Now notice how I'm not really focused on the range as much as I am on the domain. It's all about the domain. The domain are your inputs. Are all of the elements of the domain being used as an input? Yes, both B is used and both G is used. And then are they only used once? If they only have one arrow coming out, they are. They're used only one time. So this is a function. Let's use a different color to say it is a function. Let's use purple. So this is a function. Okay. each element of the domain is used exactly once. Is used exactly once. Just kind of putting it in layman's terms for you. Okay, let's come over here. Now, once again, it's all about the domain. Is every element of the domain being used? Yes, we have two elements in the domain, B and G. They are both being used. Are each one of them being used only once? Yes. So this is a function. And it is a function for the same reason that the previous example is a function, because each element of the domain is used exactly one time. Now, these are called mapping diagrams. So I'm going to write that here. Write that in. Let's write it in green. These are mapping diagrams. So if you're asked to draw a mapping diagram of the domain and the range, these are mapping diagrams. Okay, here's one for you to try. Is this an example of a function? Go ahead and press pause, and when you're ready to reveal the answer, you can press play. Okay, if you said this is a function, you are correct. It is indeed a function. Okay, let's think about domain, and let's think about the restrictions on the input due to an illegal output. Very important here. So it's so important, I'm going to highlight. So when something's pretty important, I usually take a highlighter to it so I can see it later on. So we think about restrictions on the input due to an illegal output. And right above this, I'm going to write a few things. So I'm going to write here, I'm going to make this just a little bit smaller, there we go. I'm going to write here, okay. A square root, how about an even root radical, has an issue in which we need to address. Denominators create issues that we need to address. No denominator, no radical, no problem. So kind of like no shoes, no shirt, no service. No radical, no denominator, no problem. And when there's no problem, your domain is all real numbers. So let's look at number one. Number one, there's no radical, there's no denominator, no problem. Okay. How about the second one? We're going to say no problem. Second one says y equals 1 over x plus 1. No radical. But yes, there's a denominator. That means we have a problem. And y equals the square root of x plus 5. Right away, yes, we have a radical. Therefore, we have a problem. So does the output of the expression 1 have a, what do you think we're going to write there? Think about, this is where when you're taking notes, you might want to be a step ahead of me and say, well, do I know what to fill in the notes here? Does the radical, does the output of the expression put a 0 in the denominator? So there's your denominator. Put a 0 in the denominator. That would be a problem. Why is a radical a problem? Because we can't have a negative in the radical. So does the output of the expression put I think I should say, does the input of the expression, does the input of the expression put a 0 in the denominator? Does the input of the expression put a negative in an even root radical? So those are the two things that we need to look out for. We know that we can't have a number divided by 0. So we cannot divide by 0. Cannot divide by 0. That's undefined. We're going to highlight that. Can't divide by 0. Let's make that right here. That's number 1. And then number 2, just to give you a visual, we've got an even root, whether it's a fourth root of a negative number or a square root of a negative number. These are issues because we can't have those negative radicans. We can't have those negative radicans, not when we're graphing, not when we're dealing with functions. So let's start looking at the domain. So you can see that we've got a plethora of problems that we're going to do. We're going to go through these pretty quickly, so don't be afraid to press that pause button. Okay, we have y equals 3x plus 1. I'm going to go through this rather quickly. We're looking at the denominator. Does it have a denominator with a variable in that denominator? Does it have a radical? If it has no denominator, no radical, remember it has no problem. Therefore, there's no problem. The domain is all real numbers. And how we're going to say all real numbers is we're going to say negative infinity to positive infinity. Let me highlight that. I'm going to be highlighting my answers in, let's highlight them in purple. Okay, let's look at the second one. Y equals 1 over x plus 1. Right away, this has a denominator. What input is going to give us a 0 in the denominator? Well, 1, set the denominator equal to 0. So set denominator equal to 0 and solve. That is your restriction. So x plus 1 equals 0. X equals 1, negative 1 is not allowed. So instead of going from negative infinity to positive infinity, it's negative infinity to negative 1, negative 1 to infinity. That's how we write that in interval notation, excluding negative 1. So that says all the numbers from negative infinity to infinity, excluding negative 1. Let me draw this for you real quick. Negative infinity to positive infinity, but negative 1 is not allowed. So you can see that open circle there. So we'll have negative infinity to negative 1 with a parenthesis, and then negative 1 to infinity with a parenthesis. Okay, y equals the square root of x plus 5. That's a radical. We want that radicand to be 0 or greater. So x plus 5 has to be greater than or equal to 0. So on a radical with an even index, so that even index or even root radical, you're going to take the radicand greater than or equal to 0. And that will be your domain. So x is greater than or equal to negative 5 on a number line. Negative 5 greater than or equal to, let's just do this in another color so you can see, greater than or equal to is going to be that. So greater than or equal to negative 5 would be a closed interval negative 5 to infinity. Okay, you can see that we're going to have lots of problems here to do, so we're going to go through them very quickly. Again, I just want to remind you to press pause if you need to slow down. Okay, this is a denominator, so I'm going to write denominator. When we have that denominator issue, the denominator cannot equal 0. So x in this case, set it equal to 0, and 0 is your restriction. So x can be any number except 0. So negative infinity to 0, 0 to infinity. Okay, what I'm going to do is I'm going to search for all the denominators now. And I'm going to think of just the problems with the denominators, no radicals. If it's got a radical, I'm going to skip it. So all the denominator problems, so I can get some practice here. Number 5, that's a denominator problem. If you can find the denominator problems, that's going to help you learn this. So this is a denominator issue. So we've got a variable in the denominator. We solve by setting that denominator equal to 0. Subtract 24. Divide by negative, or divide by positive 3 is going to give you a negative 8. So negative 8 is excluded. So negative infinity to negative 8, negative 8 to infinity. Okay, let's look at number 6. That's not a denominator. Number 7, that's got a radical. Number 8 has a denominator, but it also has the radical, so we're going to skip it. Number 9, the denominator and the radical, we'll skip it. Look at number 10. It's a denominator. So let's do that one. So this is a denominator. I'm going to write denominator, and I'm going to take that denominator, I'm going to set it equal to 0, and I'm going to solve. So we're going to factor. Now, if you need practice factoring, you should press pause right now, because I may be factoring a little faster than you. So this is where you want to press pause. So 2x and x, and then we're going to have a 3 and a 2. That'll be plus and that'll be minus. So I'm getting x equals 3/2 and negative 2. So all the numbers from negative infinity to infinity, excluding those two. So negative infinity to negative 2, negative 2 to 3/2, and then 3/2 to infinity. Now, I did not leave a lot of room on this for you. So you might want to use a separate sheet of paper to do some of these. It would be worth your while. Number 11, that's a denominator problem. So we're going to, and there's no radical, so I'm going to do the same thing. I'm going to set the denominator equal to 0. In fact, I'm going to let you try this one. You go ahead and try this one and see if you can get this. Press pause and then come back. Okay, welcome back. I got negative infinity to negative 1, negative 1 to 4/3, and then 4/3 to infinity. And it looks like the rest are radicals. So let's go back up to the top, number 6, and let's talk about that radical. So number 1, 2, and 3 were our basic examples. Number 1 was no problem. No denominator, no radical, no problem. Negative infinity to positive infinity is our domain. Number 2, domain, remember, those are your inputs, what's allowed to go in. Number 2, I think we all agree that x cannot equal negative 1. So how do we write that domain? Negative infinity to negative 1, negative 1 to infinity. But we went through the motions and I showed you the math, how to do that. And then number 3, what is the domain? Well, our radicand has to be greater than or equal to 0. This part is our radicand right here. The radicand has to be greater than or equal to 0. So we set up that inequality, and that actually tells us exactly what our domain is. Now this is only true on even root radicals. So if you have a square root, a fourth root, a sixth root, because remember, if you have a cubed root, you can have a negative radicand. If you have a fifth root, you can have a negative radicand. It's only when your index is even that you have to keep that radicand greater than or equal to 0. So you can have to keep it non-negative. Okay, so this is an even root. This right here is a square root. In fact, I'm going to put the square right there. It's a square root. And when you're writing your index, it needs to be in that little section right there. You can't put it off to the side, like look at number 9. You can't put it there. That doesn't mean the square root. You can't write it here. It needs to be written right there. So the square root. So this is an even root radical. So we're going to take the radicand, set it greater than or equal to 0, and solve. We add 12, divide by 3, and we get t is greater than or equal to 4, so our domain is 4 to infinity with a closed interval. That means use a bracket. Closed interval. Okay, you go ahead and try number 7. Number 7, we'll make that a try. Press pause and then come back. Okay, welcome back. This is an even root radical, so we've got negative 5x plus 1 has to be greater than or equal to 0. Negative 5x is greater than or equal to negative 1. And then dividing by negative 5, we have to flip the inequality symbol, and we get x is less than or equal to 1/5. So negative infinity to positive 1/5 with a bracket. Okay. We're almost done. We're filling in the grid. You can see we're filling in the grid. We're going to do number 8 now. You can see that number 8 and number 9 look very similar. Actually, no, number 12, we need to keep going here. Even root radical, no denominator. Number 6 was an even root radical, no denominator. Let's do number 12, even root radical, but no denominator. So what are we going to do? We're going to take p squared minus 25, and we're going to set it greater than or equal to 0. Well, that factors to be p plus 5, p minus 5. And now you might recall from the previous lessons that we have to make a number line. We've got negative 5, we've got positive 5. We've got 3 intervals we need to check here. Okay. We know that if we put a negative 5 or a positive 5 in, it's going to create that equal to 0. So those are going to be closed intervals. I'm going to try a negative 10. If I put a negative 10 in, and I can go straight here, negative 10 squared is 100. 100 minus 25 is greater than 0. That is true. If I put a 0 in, 0 squared minus 25 is negative 25, and that is not greater than 0, so that is false. And then if I put a 10 in, to p squared minus 25 is greater than 0, we're looking at this inequality right here, we get a true statement. So our answer includes 2 intervals, right, with closed intervals, 2 intervals that are closed, negative infinity to negative 5 with a bracket, and then 5 to infinity. Now we've got 8, 9, 13, 14, and 15. 13 looks just like number 12. So let's have you try that one. Go ahead and try 13 and then come back. So I set 4x squared minus 1 is greater than or equal to 0. I factored it just like we did in a previous lesson. And I got negative 1/2 and positive 1/2 as my critical values. And when I tested values, I got true, false, true, including negative 1/2 and positive 1/2. So my answer is negative infinity to negative 1/2, and then positive 1/2 to infinity. Okay, so that leaves us 4 problems left here. 4 problems. We've got number 8, number 9, 14, and 15. 8, 9, 14, and 15. So what's different about 8 and 9? Well, 8 and 9 have a radical and a denominator. So when you have a radical and a denominator, you have to apply both rules. So this is an even root radical. So that means that 2x plus 8 has to be greater than or equal to 0. However, because we're in the denominator, we cannot equal 0. So when you have that even root radical and in the denominator, your radicand has to be greater than 0. It cannot equal 0. So we take 2x plus 8 is greater than 0. 2x is greater than negative 8. X is going to be greater than negative 4. When you put a negative 4 in, 2 times negative 4 is negative 8. And I'll have the square root of negative 8 plus 8, which is the square root of 0, which is 0. And I can't have a 0. So negative 4 is not going to work. However, anything greater than negative 4 will work. So let me show you. If I put negative 3 in, that's greater than negative 4. 2 times negative 3 is negative 6, plus 8 is the square root of positive 2. The square root of positive 2 is not 0, and it's very easy to find because we don't have a negative radicand. So plug it into your calculator and we get a real number out. So this is a real number, and 1 is allowed to be divided by any real number. Real numbers are encouraged in the denominator. Therefore, our answer here is going to be anything greater than negative 4, but not including negative 4. So greater than negative 4, but not including negative 4. So that would be a parenthesis, negative and 4 to infinity. That's our domain. Okay, you go ahead and try on number 9. See if you can get the answer. Okay, welcome back. Hopefully you have 4x minus 3 is just greater than 0, meaning x is going to be greater than 3/4. That's going to be an open interval, 3/4 to infinity. And our last two, remember, we're looking at radicals and denominators, and when we're looking at radicals, we're looking at even root radicals. Number 14 is not an even root. So this is an odd index of 3. Therefore, the radicand can be positive or negative. All real numbers will work. So how do we write all real numbers? Negative infinity to infinity. And number 15, if you try number 15, see if you can reason out exactly why. why your answer is what it is. Okay, welcome back. This was a try. Looking at number 14, you probably said, well, it's negative infinity to positive infinity, but think about why it's negative infinity to positive infinity. It's negative infinity to positive infinity because it has an odd index, and x minus 2 can be positive or it can be negative. It can be any real number. Therefore, watch, x minus 2 has to be less than infinity but greater than negative infinity. It can be any value in between. So when you take infinity plus 2 or negative infinity plus 2, infinity plus 2 is still infinity. And negative infinity plus 2 is really negative infinity, because you're talking about such a large number that, you know, infinity is not a value that you can really attain. It's not a value at all. It's an idea. It's a number that just keeps going. So when you get to be that a number of that magnitude, adding 2 means little. It means very little. So therefore, x is any number between negative infinity to infinity. Well, I hope you enjoyed this video. It was rather long, explaining about functions, whether it's a function, and then also finding the domain. We continue this work throughout our remaining algebra classes, so being able to identify that domain and calculating it is super important.